Yes, so this is the penultimate talk of this series, and yes, it's Thanksgiving, just irrelevant extra fact. And so I decided I wanted to talk a little bit about something that's just fun having to do with the topic at hand, which is species and their generating functions. Because although there's a lot of theory involved, connected to category theory, for example, there's also just a lot of really fun examples, and Combinatorics is sort of famous for having like lots of fun examples that you can get to grips with. And so if I only taught you a bunch of abstract theory about how categories were connected to it, it wouldn't really get to the point. So let's do a puzzle. So here's a puzzle. So let's take a function and work out its Maclaurin series. So it's this, or Taylor series, or whatever you want to call it. So e to the negative x. Yeah. So, I'm in trouble now. I'm sorry. Yeah. So Maclaurin series is the special case, I guess, of the Taylor series, where you're expanding about the origin. And for some reason, I tend to say Taylor series, but now I regret having ever done that. So here's a function, e to the negative x over 1 minus x. So it's analytic, except that x equals 0, x equals 1. So you can expand it in a Maclaurin series, and you'll get some coefficients, which I'm going to call dn. So then the question is, what are those numbers? What is dn? So of course, the obvious way to try to do this is you just start differentiating this thing, and you try to figure out the pattern. But there's a different way to go about it, which is to say, hey, this could be the generating function of some species. So there could be some kind of structure that you can put on finite sets, such that the number of ways you can put that structure on an n-element set is dn. And then you say this function here is the generating function of that species. So let's try to do it that way. So this is just like a strategy or a guess. So let's find a species D. So technically, it's a functor from the groupoid of finite sets to the category of sets, such that its generating function is that function that we're after. Yeah. So let's try to find a species which has that generating function. And then, well, what does that even mean? It just simply means that, remember, n is the set with n elements here. You stick it into D, you get the set of structures that you can put on an n-element set. And we're saying that it's the number of them is dn. So if we can do that, we'll not only get some kind of formula for these coefficients, dn, but we'll have a combinatorial interpretation of what they are. Okay, so to do that, well, then we have to think about we should think about these other guys. There are two guys, a numerator and a denominator. So for example, well, okay, so that's the question. So what about 1 over 1 minus x and e to the negative x? So let's think about 1 over 1 minus x. So 1 over 1 minus x has a very famous power series. It's the geometric series. And so if we're trying to have this be the generating function of some species, well, we have to think about it the correct way, the generating function always has this n factorial in the denominator. So we have to have an n factorial in the numerator as well. So this could be the generating function of any species for which there are n factorial ways to put that structure on an n element set. So this is generating function of some species f if the number of ways you can put that, the corresponding structure on an element set is n factorial. So somebody tell me some kind of structure you can put on finite sets such that there are n factorial ways to put it on an n element set. Yep. Yeah, you could, or you could list them or totally linearly order them or totally order them. So in fact, there's more than one answer to this, more than one very nice answer to this question, and that's one of the ones I had in mind. So we could let f be the species such that on any finite set, what you get is the set of, I guess I'll call linear orderings of that set, or ways of putting them into a list. It's just another name for the same thing. That's right. There's another really famous species that has the same generating function. What are there n factorial of for an n element set besides the first answer? Okay, you want to get the right answer, so you're going to keep. No, it's fine. It's fine. Yeah, permutations, right? So that's a different species. Yeah, so just guess just in my role as a mathematician to like say everything you say a different way than you just said it. So I won't call them permutations. I don't know why, just because I'm perverse. They're just, but that's all I mean. But maps from the set to itself that are one-to-one and onto permutations. That's right. So an interesting thing about this is that, so although they have the same generating function because the cardinalities of these two sets are both the same size, they're not the same as species. That is, they're not isomorphic as species. So in other words, what I'm saying is that there's no natural isomorphism between these functors. In other words, there's no natural way for me to give you a linear ordering of a set and for you to spit back a permutation of that set and by natural, I mean without making any extra choices. So if you already have in mind a linear ordering of a set, then you can turn any other linear ordering into a permutation, the permutation needed to rearrange the original ordering to get the new one. And if you already have that linear ordering, you can conversely turn a bijection into a new linear ordering. But that's what we call unnatural because you've broken the symmetry of the set by picking this linear ordering. A linear ordering completely breaks all symmetries of a set. You just know a name for every single element, so you can do whatever the heck you want, right? So this is an example of how we lose information when we take generating functions. Okay, so I'm going to, well, let's see. Maybe I'll regret it, but right now I'm going to defer judgment as to which one of these approaches I want to use for what we're trying to do. So what we're trying to do is take our original equation and rewrite it in terms of species. Let me give these better names. Let me call this like linear orderings of S. And let me call this one like permutations of S. Because calling them F and G is not going to be very memorable. So, okay. Now what about, okay, so that's that. What about, huh? Hats are missing. Uh-oh. So what about, thanks. So what about e to the negative x? What's that the generating function of? Okay, Tom, you want to answer. Tom's making a really interesting face, but he's not, no one can see it except me.
Minus signs in it.
It's got minus signs in it. It's not, can't be the generating function of any species because there's nothing that has cardinality that's a negative number. Well, of course, there wasn't anything that had cardinality that was a fraction until we invented groupoid cardinality. So you might try to bend the rules somehow, but this is, but let's not. Okay, so this is not the generating function of any species. Because it has, its power series has negative coefficients. Okay, well, that suggests that we were doing something slightly suboptimal. So what we were doing, remember, is we were trying to take this function e to the negative x over 1 minus x and have it equal the generating function of some species yet to be determined called D. And this is a generating function of something, but this was not. So the obvious thing is just to multiply both sides by e to the x and get it onto the other side of the equation and not deal with e to the negative x with that annoying negative sign in there. Okay, so let's think about it this other way. So in other words, that equation is equivalent. This 1 over 1 minus x equals e to the x e hat of x. And so let's see if there's a species whose generating function is e to the x. So can we find a species whose generating function is e to the x? So e to the x is 1 over n factorial times x to the n summed over all n. So this is, if this is a generating function, and I think if you remember it carefully, I've already told you about this, but if this is a generating function, then it's the generating function of some species such that there's just one way to put the corresponding structure on an n-element set. So what is that? What, are there lots of such species? If so, we'll name one. So think about it while I write some stuff. I.e. a species H such that the number of ways to put that type of structure on any n-element set is just, or any finite set, is just one. Well, yeah, Yeah, it's a structure it's a very boring structure that you can put on any finite set in just one way. You could call them the number of one colorings of the finite set. Yeah, but there are many ways to talk about it, I suppose. You could call it like the number of complete graphs on the finite set. There's also one of those. But all those species are in fact isomorphic to each other, because it's very easy to get isomorphisms between one element sets, right? And they're natural. There's none of this fishiness that we had about like picking an arbitrary choice. So there's just one such species. There's one such species up to isomorphism. Ah, sorry. Yeah. And remember, I talked about some kind of, so a species is a kind of structure you can put on a finite set. But if there's at most one way to put that structure on the finite set, we tend to not call it a structure. We tend to call it a property. So for example, I talked about like the species being an n-element set. That's something you can put on an n-element set, or being a 5-element set. You can put it on a 5-element set in exactly one way, and for any other number of elements, you can't do it at all. And so this is like that, but you can put it on any finite set in exactly one way. So we could just call it, and if you're really niggly, I'd say up to isomorphism. So this is called, I would call this being a finite set. That is the structure that you could put on finite sets. That's just being a finite set. So there's one way to do that. Okay. Yeah. So in fact, I had talked about it before, and I called that species X for the obvious reason that its generating function is the exponential function. So there's this interesting relationship between the exponential function, which is a mildly interesting function, and this completely boring structure you can put on finite sets, which is ELF. Generating function of this is e to the x. Okay, so I think we're sort of there. What do I mean by that? So somehow something about these boards is not working right, especially since I'm trying to like always make sure that the board that I want people to read is on top. But we had this equation we were playing around with, which most recently looked like this. We were trying to find some species d whose generating function times e to the x is 1 over 1 minus x. We saw there's a nice species and really just one whose generating function is e to the x with a hat. And then there's this unknown species we wish we had. And then, well, we have a couple of choices of species whose generating function is this. So we saw that this 1 over 1 minus x was the generating function of the species of permutations, or also the generating function of the species of linear orderings. So we have two choices of where we could go with this, but the idea that we should try to use is that when one generating function is the product of two other generating functions, that would follow from the fact that one species is the product of two other species. Remember, we came up with this way of multiplying species such that when you take the generating functions, you wind up multiplying the generating functions. So this will follow. This will hold if it's a one-way implication. This, what I'm about to say will imply this. This would hold if the species, for example, perm, is isomorphic to the species exp times this mystery species D. But we don't know for sure that it's perm that's the one we want to use. Maybe it's this linear orderings. So let's figure out if either of these actually work. Well, I need to remind you what this multiplication of species amounts to. To put an exp times D structure on a finite set means to take that finite set, let's call it S, and to chop it into two disjoint parts. And then on the first part, you put an exp structure. That is to put a this boring structure being a finite set structure on it. That's why I like, what is that? Why am I going to draw that? Well, okay, there's no, so so we put the boring structure that you can only put on in one way on this first part, and then you put a D structure on the other part. And unfortunately, we don't know what D is yet. So, but the point is that this is how product of species works. To put an F dot G structure on a finite set, you chop up the finite set in any way you like into two disjoint parts, whose union is the whole thing. Put an F structure on the first part and a G structure on the second part. So this is supposed to be the same thing. To do this is supposed to be the same thing as doing this. Well, unfortunately, we don't know which one. So now we need some intelligence to guess which one, and also to guess which D. Does anyone have a guess? So like, can you describe a linear ordering of a finite set as first you chop the set into two parts, then you don't do anything at all with the first part, and then you do something with the second part? That doesn't sound right to me. How am I supposed to do it? I'm trying to linear order the people in this class, and I say, okay, the way we're going to do it is we're going to arbitrarily divide into two parts. Those guys we're not going to do anything with, and for these, we'll do something. There's no way that's going to linear order you, because like there are all these guys I didn't do anything with. We're not going to learn how, yeah, so that doesn't, that's, nah. Yes? Ah. That's much more promising. That's much better. So if I have a permutation of a finite set, any permutation of a finite set, I'm trying to draw the same looking finite set here. I can always take any permutation of a finite set and say that permutation will consist of, well, there will be some elements of my set that are mapped to themselves by the permutation. They'll be called the fixed points of the permutation. And then there's the rest, the points that aren't mapped to themselves. So they will get mapped to various other things, and they'll form various cycles. And you see that now it's working. So perm is what we want. And so to put a permutation on the finite set is exactly the same thing as chopping it up into two disjoint sets any way you want, saying that the first guys in the first subset are fixed points, and the guys in the second point have some permutation of them with no fixed points. Please ask a question if there's anything unclear about that, because this is like the high point of the well, it's not the high point in the sense of results, but it's the high point in the sense of like getting the idea. So we have, so it is indeed true that perm is isomorphic to x dot d if d of s, put a d structure on a finite set S, is to get a bijection from S to itself with no fixed points, with no x in S such that f of x equals x. So great. So those kind of permutations, do you have any questions? I really want, some people were like looking at me in this sort of growly way that mathematicians do when they're chewing on a bone. Yeah?
So I sort of see where the number of ways you could put x on one set and b on the other, on another way. You could split a set into two parts and put one structure on one and another structure on the other. The number of ways to do that is the product of the ways to do the one to the one and the other.
Yeah, notice that the number of ways that's like a unenlightened, decategorified attitude here. We're not just asking for like the number of ways, because like the number of linear orderings was the same as the number of permutations. We're talking about like, can you establish a natural bijection between them? So what I'm saying when I'm saying this is I'm saying that on the one hand, if you give me a permutation, I can get from it a way to chop that. If you give me a permutation on a finite set S, I can give to you a way of chopping that set up into two subsets and a way of not doing anything at all to the first set and putting one of these kind of permutations on the second one. So like you give me this, and you had conveniently drawn the wiggly line, and I say, oh, look, here are these points that are the fixed points, here are the ones that are not. I extract from that. Now I know what, by the way, now I know what D actually looks like. I extract one of these permutations with no fixed points on the second subset. Okay, and then conversely, if you give me any way to chop up a set into two parts, that's what the times is doing, and you give me nothing interesting about the first part, and one of these permutations without fixed points on the second part, then from that I can get a permutation, and that those two processes are inverse to each other. Yeah, so it's much better than just like counting the number of two things and seeing that they're equal. It's you have like a systematic procedure for going back and forth between those two things. It will imply that the number of permutations is equal to the number of ways of chopping the set into two parts, doing nothing to the first part, and doing this other thing to the second part. And counting the numbers of the second things is our ultimate goal here, remember. That's what we're engaged in.
I guess I think you're trying to.
Sure, yeah, no, say it.
So maybe that how I'm going to stop the set. I define that quality. It's not that I get to choose any division that I want on the right hand side. It's that the element of term that I choose on the left hand side may force it.
It will force a specific way. Yeah. So if you start with a permutation, it forces a particular way of chopping things in half. But then conversely, I can take any way of chopping things in half, doing nothing to the first half and putting one of these fixed point free permutations in the second half, and that determines a permutation. So yeah, right. Yeah, so the chopping in half is sort of in there. This doesn't know anything about that. Yeah, it's interesting how it works like that. Yeah. Okay, so therefore, we figured out an interpretation of these coefficients of our power series. By the way, what are these things called? It gets very tiring to say this long phrase over and over again. These are called derangements. So they're like rearrangements that completely move everything around. So these are called the derangements of S, which leads to all sorts of great jokes, right? So like, you're completely mixed up, you're deranged. So yeah, so what we've seen concretely then is that this function that we started out wondering about the Maclaurin series of, we started wondering what those coefficients were. Now we know something about those coefficients. Dn is the number of derangements of an n-element set. So that's something I think that would be a little bit hard to figure out, maybe, just by taking this and starting to do the Taylor series and stuff like that. You'd probably eventually figure it out, but this, I think, is like a better way to do it. However, you could still be unhappy because we have, in some sense, calculated dn and given this formula for it. But it's still, if I ask you, like, okay, so why is asked, what's d5? You'd still go like, oh no, I have to permute a 5-element set in all 120 ways and find the ones that have no fixed points. That's still, so there's still something unsatisfying about where we are. Luckily, it's not bad. We just need a different way of calculating the number of derangements of an n-element set. Now that we know that's what we're after, we can start thinking about it in various ways. And here's how we can do it. We can use what's called inclusion-exclusion. So inclusion-exclusion is a way of counting where you count things in a way which may double count things and may triple count things and so on. And so you just forget it, you just count them, over counting them. Then you subtract off the number of times you've double counted things, the number of pairs where you counted the same thing 2 ways. But then you may have subtracted off too much because there were the things that were triple counted. So then you add that back in, and then you subtract off, Let's just do it. So dn is, okay, so I'll start with the number of all permutations. That's obviously an overestimate. Then now I want to exclude the ones that have fixed points. So how am I going to remove off the ones that have fixed points? I'll do it a really stupid way. I'll say, like, okay, I've got this set. It has n elements. Now I'm looking for the permutations that have a fixed point, and so that I can count them out. So I'll just, well, there are n different choices of what the fixed point could be. So minus n times. And then I could just look at all permutations of the remaining ones. Now that's not so hot if you stop there, because if you notice, that's actually n factorial and we're down to 0. So that, obviously I did something stupid there. And what I did stupid was that I subtracted off too much, because basically the reason why is that it's not true that every permutation has at most one fixed point. If every permutation had at most one fixed point, then this would be good. I could go through and say, oh, if this is the fixed point, then the rest could be permuted any other way. But the point is there could be several fixed points, and so then we're like we've subtracted them off multiple times. So that's no good. So okay, so now let's add in, to correct for that, the accrued count of the permutations that have 2 fixed points. So okay, if there are 2 fixed points, at least 2 fixed points is what's actually going on, then there are n choose two ways of picking what they are. And then I'm going to again be sloppy and say, okay, and then the rest just get permuted however the heck they want to be. So this is like, these are the ones with at least one fixed point. Now we're adding back in the ones with at least two fixed points. And so on. So we just keep on going like this. Well, you see what the pattern is. And then eventually, and I can't tell you whether it's plus or minus because it depends on the parity of n. Eventually, you're going to get this case where they're all fixed points. So you've chosen all of them. And then there's nothing left to permute. That term is at least correct, right? There's one way for the to all be fixed points, and this is working out to equal 1. So this is actually correct. I mean, so if you've never seen exclusion inclusion before, you may think this is like the most unconvincing calculation you've ever seen, where like I keep on making stupid mistakes at each step of the process, and then at the end I say, so it's right. but that's sort of the joy of inclusion. Exclusion is that like you keep making mistakes in a way which you prove compensate for each other. And you can just look up like Wikipedia or anywhere the general inclusion exclusion formula and the proof of it and see that it in fact works. So this is great. So let's see what this is. So one nice thing is to think about this in the following way. Well, this is just n factorial. But then when we get going here, let's use the formulas for the binomial coefficient. So this is n factorial over 2 factorial n minus 2 factorial times n minus 2 factorial. And you can see that something nice is happening, and I should probably do another term, n factorial over 3 factorial n minus 3 factorial, and then times n minus 3 factorial plus. So that's the kind of way it goes. Whoops. Thanks. And then we get down here to 1 at the end. I'll just write it like that, although you could write it some fancier way. And so this obviously simplifies because of the cancellation of the stuff in the denominator from the binomial coefficient. So what we're getting is n factorial minus n factorial plus n factorial over 2 factorial minus n factorial over 3 factorial plus and then plus or minus, well, you can think about it this way, n factorial over n factorial. That's what this 1 is. What?
3 factorial.
Ah, thanks. So that's getting to be pretty nice, and clearly you want to factor out an n factorial here. And you get 1 minus, well, let's be cutesy, 1 over 1 factorial plus 1 over 2 factorial. I mean, I would not so if I was really cutesy, I'd do 1 over 0 factorial, like that. I'm not that cute. And then depending on the parity of n, plus or minus 1 over n factorial. So that's pretty cool. So the question becomes, what is this thing? You know a bunch about this thing, probably. I see he's waggling his eyebrows in a knowing manner, the way mathematicians sometimes do. So someone tell me something about that. Come on, is it like beneath your dignity, or is it above your dignity?
Roughly 1 over e.
It's like roughly 1 over e. Yeah. So this certainly approaches. This approaches 1 over e, which is very nice. Yeah, because just the power series for e to the negative 1 will give you that. So one interesting thing is we're seeing that in the limit where n becomes large, the number of derangements is about the total number of permutations times 1 over e, or divided by e. So one thing we instantly see as a kind of side fact, which is not the exact count of dn, but an interesting fact that is that one way to put it is this, is that the limit as n goes to infinity of the number of derangements of an n-element set divided by the number of permutations is 1 over e. So this is sort of cute. So the way I like to say it is, if like, suppose you're at like a huge conference of mathematicians and you all go out to a bar and you all hang up your coats at the bar, and then you get all completely drunk and you get completely confused and you all just randomly grab a coat off the hanger. Then what's the probability that nobody gets their own coat? It's about 1 over e. So that's interesting. And that also connects with the word derangement in a nice way. So you can talk about like large conference of deranged mathematicians. So yeah, so that's neat. But then there's something even better, because we can actually use this, this same formula to sort of, in some sense, exactly calculate dn instead of just this asymptotic way. Because, see, if you look at what we're getting here, we're getting, how to put it? Yeah, I guess I'll put it this way. So if we look at n factorial over e, which is this approximate formula for dn, that's not quite the way I want to say it. What am I trying to say? What I'm trying to say is that, yeah, I'll just say it. So this is an alternating series. So you know that the error, the difference between 1 over e and this thing, is smaller in absolute value than the first term that you left out, right? So we can actually, we know a lot about what's going on here. So the difference between dn and this partial sum, it's going to be less than or equal to the first term that we left out, which would be where we had an n plus 1 coming in. So it would be less than n factorial over n plus 1 factorial. N factorial because of this, n plus 1 factorial is the first term that we left out. Yeah?
So you've got dn, which is like about n factorial, and
Yeah, sorry.
multiply that thing in round bracket by n factorial.
Yeah, thanks. Right. Yeah. Right. So I'm trying to see how close that approximate. I did. What am I trying to say? Sorry, I'm trying to, okay. That's not what I meant. What I meant to say is that okay, let me try to say it right. If we add this stuff up forever, if we go on forever, not stopping here, we get 1 over e. So we would get n factorial over e. That would be the infinite sum here. This is the partial sum. The error in approximating the whole sum by the partial sum, because it's an alternating series, is at most the size of the first term that we omitted, which is n factorial over n plus 1 factorial, which is 1 over n plus 1. And the point is, of all this nonsense, is that that number is smaller than 1. I guess smaller than a half as soon as you get going. If n is what? Yeah, I know I'm cutting it close here, but I want it to be, I'm wanting it to be, I think that I think that there's something I could say that's actually just always true, not even just for small cases. But what's the point? So the point is that this here is an integer because it's just the number of derangements, so it's an integer. And we're saying that this integer, its difference from n factorial over e, is smaller than a half. So it's the closest integer to n factorial over e. So this is a nicer formula for dn. And I just seem to get nervous now that it's like maybe only true when I don't need bigger than 2. First of all, I just need it bigger than 1, right? So, huh? If it was right halfway between 2 integers, I'd get very nervous if I was talking to know what's the closest one. So let's make this be less than 1/2. Yeah, so I don't know. I seem to be getting that this is true if n is bigger than 1, which I think
It's true for 1 as well.
it just happens to be true for 1. Okay, how many derangements are there of a 1-element set, everybody?
0.
None. Which is that the closest integer to 1 factorial over e? Yes, it is. Okay, so for some reason, my estimate was like suboptimal. And in fact, also 1. What about 0? Sorry, now I'm getting a little silly, but how many derangements are there of a 0-element set? 1. Yes, there's no fixed points of any permutation of a 0-element set. So so d0 equals 1, and I don't think that that's the closest integer to 0 factorial over e. Okay, so you do have to be a little careful. Not that you ever cared about that, such a low case. You probably wouldn't have thought about it if I hadn't brought it up. But anyway, so like now you see with this type of formula, well, as long as you have a good way of calculating n factorial over e, you can rapidly calculate the number of derangements. So what was fun about this type of argument, you see, is it uses a kind of mixture of reasoning. So first, we used what is really category theoretic reasoning about species to notice that there's this structure you can put on finite sets that gives you, that counting them gives you the coefficients of your Maclaurin series, which happen to be this funny function here. And then once you know that combinatorial interpretation of those coefficients, you can go to work and try to calculate that in other ways. And that was this sort of second phase of the operation. The second phase of the operation, notice, involved a whole lot of subtraction, whereas the first phase, because we don't know about negative sets or sets with negative cardinality, I am not able to carry out the whole inclusion-exclusion argument using species. Now, maybe Tom could, because Tom has a way of calculating the cardinality of a category that can be negative. And in fact, I think I'll just give him credit for it. He certainly knows that you can do this trick called Möbius inversion using that formalism. And I believe that you can think of the inclusion-exclusion argument as a case of Möbius inversion. So maybe there is some way to carry out the whole argument up to this alternating series before you go ahead and start taking cardinalities of things. And I think that would be lots of fun to do. But anyway, so I'm gonna quit here, and then next time I'll just say, one thing we haven't done with species is we have not differentiated any power series and see what that corresponds to in species, nor have we composed a power series with another power series and see what that means for species. So those are the other two operations that you can do, that besides the one that I've talked about, two other main ones, and you can solve other fun problems with that. And I'll just see what I can do in 50 minutes.
That'll be the grand finale.
The grand finale, yeah, I know. I need to, for the next week, I have to like figure out how to make it actually end with a bang instead of a ugh. Okay, thanks. Are there any comments, questions? Yes?
Yeah,
No, maybe not, because I don't. Uh-huh.
So in combinatorics, in some combinatorics, talk about involution.
I don't know. No, I don't. I don't know that by that name. What is it?
So alternating series, number of fixed points, essentially a sign reversing.
Sign reversing.
Color a set, what is that, a 2? Or you color with pluses and minuses?
Oh, an involution that maps all the pluses to minuses and vice versa.
Alternating sum counts the number of fixed points. It's all the things that don't change.
Wait a minute. If it maps pluses to minuses, how could there be a fixed point? Sorry, I'm saying some.
There can be fixed points that don't do that. So you basically kind of break it into 3 parts.
Oh, it's an involution. So it'll have fixed points and then other points that come in
Exactly.
pairs where they get switched with each other, and you color one of them plus and the other minus. I see.
And then
Huh.
residues
Yeah, no.
get wiped out,
Hmm.
and whatever fixed
Uh-huh.
points,
Cool.
stick around.
Uh-huh.
You can use this to prove inclusion and exclusion.
Okay, that sounds weird.
So
Okay.
cool.
Yeah, uh-huh.
And I've been working with students various things on programming going on with Phillipe.
Uh-huh.
But I guess so. I was kind of expecting to go, aha, I know what you mean. But yeah, you have cycles and
Uh-huh.
things don't change, and then you have things that are things that change, and you have things that don't change, that fixed points.
Uh-huh.
Um,
Yeah, and I'll have to look into that.
So it sort of seems like you're either the mindset. I was actually very cool. It's almost like you say, take your set, split it into 2 things, and then sort of do inclusion and exclusion is the like structure you put on. Right? I it's kind of done,
Uh-huh.
right?
I'll have, yeah, I don't can't say anything too intelligent about that, but I'll have to try to learn about that. One thing makes me want to mention is that I've been talking about structures you can put on one set, but you can also do multivariable species, talking about structures you put on 6 sets, for example, and then you would get power series in 6 variables, counting the number of elements of each of those 6 sets. And so since you were like very quickly taking your set and chopping it up into some guys called pluses and some guys called minuses, it might, and then maybe like a third bunch, which are like the fixed points. So yeah, so like one thing you could do is like cook up a 3 variable generating function for those, where you have the number of pluses, the number of minuses, and the number of others. And that type of thing can be very useful all over the place. I have a bunch of web pages where I was talking about properties of random permutations. And there's all sorts of really fun questions about random permutations, like what's the average size of the largest cycle of a randomly chosen permutation and things like that. And you can solve a lot of them using generating function techniques, but you often want to use several variable generating functions to solve them. By the way, I found that whole subject incredibly fascinating, because before then, I never thought about what an average permutation of a large set was like. And so I had no intuition for what it was like. So I'll just tell you one fact about it, which like changed my life, which not guaranteed to change your life, is that there will typically be on average, it'll be like one cycle that's over half of the points are contained in. It's called the giant cycle. And if there's one that's bigger than half, then of course there cannot be another one that big. So basically, also the average number of fixed points of a random permutation is 1. So things get mixed up a lot more than I thought. I thought like, oh, there'll be lots of little bunches, but no, it's not that. It's like one giant cycle. So anyway, all that stuff can be shown using these type of techniques with a multivariable enhancement. Yeah.
Is the idea that every Taylor series that has almost an fairly positive, should not all non-negative coefficients can be interpretable as some
It can, but it may be a very stupid species. So for the reason why is that for any Maclaurin series where the coefficients over the n factorials are non-negative integers, I can make up a species like this. I'll just say that for an n element set, I'm going to say that there are like a sub n ways to put this structure on it. And the way that those structures transform under permutations, which is the way I have, that is going to be trivial. So in other words, like if I want the number to come out to be 5, I could say like, I'll color all the points in my set, either red, green, blue, indigo, or violet, or whatever. And so there you go. But the problem is that those type of species are pretty useless to work with. So it doesn't really do much for you.
I'm going to stop recording now. I need to leave.